Welcome. Thank you for joining us. My name is Matt Toon. I'm here with my colleague Aldi Arari, who are based in the UK. As part of over 40 simulation engineers within the TECHNIA Simulation Centre of Excellence, our role is to support customers with simulation solutions in the UK and the USA. We support the full simulation solution portfolio from Dassault Systèmes to include structural, thermal, CFD, electromagnetics, optimization, etc. Our approach is always driven from our team's experience, as their day job is using the tool sets to solve real engineering problems. Also joining us later in the presentation is Graham Short and Jake Taylor from the TECHNIA Simulation Centre of Excellence.
Right. Today we are going to talk about why you should use simulation early in the design process and why this practice will deliver far better results in the long term. Let's have a quick look at today's agenda. We will start by setting the scene, then we will go into what is MODSIM. It's not a software application. Why should you adopt this process? Then we get into the benefits and how could TECHNIA help you. So, who are we? TECHNIA is a global partner for Dassault Systèmes with offices worldwide. As mentioned, TECHNIA have put together a Center of Excellences, which include simulation, engineering, and manufacturing, which all specialize in these fields. These are made up of colleagues who practice their profession daily and sharing their valuable knowledge with you, our customers, either as a service or support and training for our software solution. So, what is MODSIM? Is it a software solution? Is it an ideology? Matt, can you explain, please?
Yes, no problem, Aldi. We've all heard it being said you need to validate your design with simulation. Quite often we experience that simulation specialists are utilised just to check if a design works, pass, fail, or not necessarily used to drive innovative design. So what about all those engineering decisions that you've already been made? How are they validated? Is there a weakness in the design already which may not be discovered until much later, or worst case, with a failure in the field? We need to start shifting our focus to explore the non-obvious, non-intuitive solutions to gain market advantage and improve our designs. Here's a quick video in less than a couple of minutes that sums up the MODSIM workflow.
Experiencing your design is made possible through seamless concurrent engineering and simulation that begins at the earliest phase of product development, enabling you to deliver the right product at the right time. When products were simple, engineering was simple. However, the increasingly complex connected products of today require engineering teams to stay one step ahead by understanding and predicting product behavior as early as possible in the development process. CAD and CAE technologies have evolved. However, engineering practices and workflows have not kept pace. Most modeling and simulation functions today perform as specialized, siloed disciplines, with each using separate, often incompatible software tools. When a designer shares information, that information must be translated and reworked into simulation software. Rigid handovers to analysts slow down collaboration, disrupt innovation, and prevent companies from timely delivery of these more sophisticated products without additional resources. What if you could break down the walls between disciplines and free analysts and designers to innovate in harmony? Integrated modeling and simulation, or MODSIM, makes it possible. MODSIM is a lean approach to engineering that can revolutionize the productivity of engineers and product teams. Seamless engineering, using one model and starting at the earliest phase of product development, allows engineers to confidently deliver the right product at the right time.
So at this stage, we need to clarify something. MODSIM is not a software tool, it's an engineering process.
Okay, let's try and illustrate this in a different way in terms of cost evolution for a particular project. This displayed graph shows an example from a major OEM. Now, I appreciate not everyone is a major or automotive OEM, but the analogy works across the spectrum. In this case, some 80% of the total time and cost of product development is committed at the early stages of the product lifecycle. If you think about your own project, then there's still lots of money committed early. However, only some 20% of time and cost has been expended. This is because fundamental decisions are made early: geometry, material, system technology, and architecture. Again, if you are making design decisions, are you validating them? For example, you design a metal component that is stamped or starts off as a flame cut blank. Are you considering the trauma the material has gone through to make that part, and then be confident that the yield of the steel has not been compromised and can stand up to the environment you have designed it to perform in? Have you inadvertently engineered in a weakness due to the manufacturing process? My colleague Graham a little later is going to show how one feature can be the weakness in a design. As the example just mentioned, should you have done some simulation to validate your design and its manufacturing process? So, a relatively minor change at this stage made in the early is inexpensive, but the same change made at a later stage can cost orders of magnitude or more. In worst case scenario, it fails in the field, and then we need to do a recall.
Thanks. So to sum up our day, so we're saying the exploration and trade-off of design alternatives through simulation has huge payoffs when applied early in the product development. So TECHNIA is working with companies to invest in developing and managing simulation IP here, as the more information maintained and collected offers huge savings when confronted with product design decisions and alternatives. This is why MODSIM is such a key engineering workflow practice.
Absolutely, yes, Matt.
Okay, so let's look at this in more detail, which I'm hoping resonates with the audience as something that happens in their business. You start off designing. Once the design has been worked through to near completion, it's thrown over the wall to the simulation team, internally or externally if you use consultancies, for example. Then the reports come back highlighting some issues. It goes back into the design for rework. Then there is a full design review, and your confidence in the design is not high. So you start developing a second revised design, doing the same workflow, hoping you are getting each time closer to fulfilling the original design brief and developing your best product to date. However, product deadlines are looming. Are you running out of time? The product is better than version 1, but is version 2 your best design? Have you nailed it? It's obvious to everyone that this workflow does work, but it's slow, it's disconnected. The threads and traceability is difficult or very manual due to different tool sets, outside influences, consultancies, for example. There is room for errors and risk. However, this is the norm. When I speak to my customers, this is what they do. I haven't even mentioned testing and failures.
So let us map this onto our earlier chart. It's obvious now that engineering changes to material, design, manufacturing are costly. The later you need it or must react. There are high risks due to weakness found late. The cost goes up. The end consumer confidence in your product drops, especially when it hits the mainstream use. Like thousands of products are recalled to change brakes, brake paddles, airbags, sensors, etc.
Exactly, Ali. Well, I know when I read product reviews and make a purchasing judgment from them, these are heavily swayed on those performances and that reliability. And I'm sure I'm not alone in this process. Okay, so what's the answer?
Good question, Matt. I'm glad you asked. Let's look at an alternative workflow to the one we have shown earlier. We have already highlighted if you could validate design changes early with simulation, then that's a benefit. If you could use tool sets that work with your CAD design team, manage the data, and link everyone together, then using simulation at the start and during the design process is a reality. This will then allow you to drive innovation using simulation. If you could run a study looking at the load criteria as well as manufacturing process, considering the structural possibilities for different design choices as part of the design process, then with no doubt you are going to get a better, more robust design than previous ones. Even if you have to make a prototype, you are confident right at the beginning it's going to work and pass.
So rather than doing a couple of reviews and reworks of the design, you're constantly moving the design forward. So you can end up with, say, I don't know, version 101, which you are confident is your best and most robust design.
Yes, absolutely. As you are improving with every engineering validated decision.
We've discussed how a MODSIM approach to a project has time-saving benefits. If this all seems daunting, then you're not on your own. As previously mentioned, TECHNIA daily practice the MODSIM process can help you in your adoption. To get you up to speed and proficient in the new way of working, TECHNIA have the expertise and know-how to help you adopt these best practices. My colleague Jake a little later is going to outline how we can accelerate this ideology.
So we have just shown how bringing simulation earlier into the design process brings massive benefits. But does this stop here, or does it grow with businesses? In fact, this is just the start of the journey. I will let Matt explain more.
You're quite right, Aldi. There is so much more we can build on. We mentioned being able to do lots of iterations of the design, and this can be automated and optimized. In the life science industry, for example, in silico or virtual modeling brings testing and the digital twin to the levels where you find your final physical test is a known result. You need to be able to control and monitor your design changes. And this is where the benefits of a PLM solution using the 3D experience, for example, can add to the value to the wider organization. Talking of the wider organization, project management is key. Then once the design is ready, it will go to manufacturing and production. All of these follow on. This can be seamlessly managed, and TECHNIA have the expertise in the wider center of excellence, as we mentioned earlier. So, what does this mean from a software point of view? As you can see from the graph, we can keep it very simple, but the most important takeaway is it's scalable for the designer's needs. Don't forget, TECHNIA is here to guide and support you through this whole journey. I will leave this up for a few seconds just for you to digest. But let me just map where Abacus sits on this. Then you can see how this all sits together. Alde will now map the scalable solution to a wider business need.
Indeed, Matt. Let's take a quick look into our simulation role portfolio that forms the basis of all of our solutions. The software configuration is mapped to industry processes and solutions. As you can see, some of these roles are more targeted towards designers and product engineers, while others are targeted towards analysts. We have scalable native portfolio for core structures and durability to fit with the appropriate engineer's role and skill. We offer specialized roles for composites and manufacturing, material calibration, while model building and meshing is included with most physics role. We also offer a standalone role for model build. We offer two native fluids roles, one for general purpose mainstream fluid markers and another for plastic injection molding solutions. We have a new electromagnetic engineer role, bringing low and high frequency electromagnetic simulation to the platform. We have a great portfolio for generative design for structures and fluids, where designers can optimize the weight, stiffness, and performance based on the manufacturing process used. We have roles for simulation process and optimization. Apart from the simulation role, every simulation starts from the design. The platform has a native 3D design apps from SolidWorks, TECHNIA, but to be honest, any CAD system will work and can be used for MODSIM. The beauty about all of the above roles, they all work from the same database and no import or export required. They are also available on either cloud or premise.
So now we've set the scene. Let's look at this from a technical point of view, starting with a simulation approach followed by a designer's approach. I'll hand over to Graham for the next step.
Okay, so thanks to Matt and Aude for articulating why MODSIM as a process and an ideology can help make better products more efficiently. Have in mind all that they have said around the technical and business case as we now move on to look at how MODSIM could be implemented in practice. In this next section, I want to take a look in a bit more detail at the kind of simulations that can be performed to generate information that is useful to inform design decisions early in the design cycle. The motivation for this is to minimize but not eliminate validation tests, prototyping loops, and mule testing, and so get to the solution faster. This is the agenda for the next 20 minutes or so, during which I hope to convince you that the tools available to do this are both robust and accurate, and also simple enough to use that any overhead to the project development timeline is an investment that will pay for itself later on. Firstly, we'll explore how we move from the abstract benefits of MODSIM as a process to where it can be most effectively deployed during the design cycle, looking at how understanding more about each component and how they work together ultimately leads to a better product. Then we'll look at what exactly is happening and if we can believe numerical models of reality at all. Don't worry, there's no maths equations, complex science, or textbooks. We'll look at a very simple example comparing structural simulation tools with a simple physical test, focusing on why and where structural simulation tools are only an approximation of reality, but also identifying how they are more than accurate enough to be a useful equivalent of a physical test, allowing significant design decisions to be made with confidence based on the structural performance. Then, having convinced you all that this stuff actually works, I hope, we'll marry up these first 2 points to demonstrate examples of where simulation can bring real value to making decisions by adding structural performance data to back up the choices that need to be made to progress a design from idea to a production item that will perform as intended straight out of the box. While we're doing that, we'll consider not just how we get more data, but how to understand what it can mean and how to make decisions using it. And finally, if that ticks a lot of boxes, I'll hand over to Jake, who will talk about how TECHNIA can help you deploy this mindset and tools at whatever level is right for you. So let's look at the first of these points. How do we move from understanding the benefits of MODSIM in an abstract way to actually seeing the benefits in practice? This could be in terms of reducing time to market, lower development costs, or simply a better product, or a combination of all three if we do things well. I think Matt and Aude make a compelling case for including simulation as part of the design cycle, not just as a specialist tool for final validation of the near production design. So how do we move from a good idea to seeing the benefits realized in practice? As has been mentioned earlier, in the context of this presentation, we're talking about building numerical structural models based on the evolving CAD geometry of the product. This may be preceded, augmented by, or run in parallel with hand calculations or other methods to inform design decisions around the structural performance and validate the results being produced by more complex methods. These simulations are likely to be at component, a small subassembly level, perhaps focusing more on the comparative and qualitative effects of changes in your design on the overall structural performance, rather than getting too deep into the details of every interaction, loading action, or material behavior. At this stage, we're still very much in the 80-20 stage of knowledge in terms of gathering enough data to try and understand a large area of the performance envelope for a small amount of effort. If we wait until the design is mature enough to create a detailed model of the complete product to find out how it performs structurally, it will almost certainly be too late or too expensive to make significant changes by then. In the example on this slide, the automotive crash example might take many months to set up and solve. The lug on the right, by contrast, may take a few minutes. The information which both provide is valuable, Both models are impressive, but the context in which that data is to be used is important to understand that. It's also worth saying that while understanding the structural behavior of a product is undoubtedly important, there's no reason why simulations of all the physical phenomena relative to the performance of the product can't be applied up front in the product design. That could be fluids modeling, electrical systems, electromagnetic simulations, as well as whole system level models. Indeed, many of these processes may be connected. Drop testing of consumer packaging is a simple example of where the fluid behavior may be coupled to the structural design and have a direct impact on its success or not, as shown in this example. This is all very compelling, you might be saying, but how can I trust that my model matches what I see in reality? At a more basic level, can I rely on that data from simulations to be as useful as physical tests? The honest answer is that it depends on how good your model is at capturing all of the physics that is in action in reality when performing your test. And I think you can appreciate the amount of physics at work in the example we show here. A corollary of that statement is that the more complex your test, the more complex your model has to be, and the more likely that it won't match reality first time. The flip side of that statement is that the simpler your model is, the more likely it is to be a good proxy for reality without extensive validation. The underlying physics for material mechanics and the methodologies for solving the equations that define these models are sound and well developed. Couple this with the power of computers to do the heavy lifting, and the ability to solve ever more complex models of reality exists. Or, as we want to advocate here, you can use the power of the tools and computers to build and solve simple numerical models very quickly indeed. This doesn't unburden the user of a responsibility to consider all of the input assumptions and the results with a guilty until proven innocent attitude. But the simpler model, the less modeling decisions need to be made, and the lower overall complexity means there is more chance of the model providing useful results quickly. This is the pretext for a MODSIM approach to deploying simulation alongside design. Still don't believe me? Well, I'll prove it to you. Let's take this simple structural problem of a bar of steel subjected to some bending load. We want to know how much the bar bends at a given location for a given load at another location. This isn't a contrived validation example from a software supplier. This was set up a few days ago as a blind test for the purposes of this presentation in a secret test facility in Oxfordshire. The steel bar is of a known rectangular section. It's been clamped to a workbench on what we are assuming to be a relatively rigid foundation, and a load is applied at a known position along the bar's length from the clamping point. The vertical displacement due to that applied node is measured at another axial location. As physical test goes, it doesn't get a lot simpler, but there are still things to think about when extracting even this problem. Geometrically, the problem is easy to define. The bar has 3 primary dimensions and 2 additional reference dimensions for the load and measurement points. The CAD model to define this in 3D will be the work of a few seconds. When it comes to defining the structural simulation, we need to think about a few other things though. How the bar is fixed is an important consideration. One of the clamps has been placed adjacent to the end of the steel support, so it's probably reasonable to assume that all of the bar restrained by the clamps cannot move. As such, we don't need to model that and can assume a fixed boundary condition adjacent to the clamps. The material under the clamps, we assume, cannot move, and so doesn't affect the deformation of the bar elsewhere along its length. This fixed boundary is an idealization. Nothing is infinitely rigid in reality, and neither are the clamps. But the clamps are very stiff relative to the bar, so it's a good enough assumption for now. At the loading point, the mass acts over a finite region, centered on the loading point itself. We could model the mass and its interaction with the bar, but that would likely be overly complex for our purposes. We can work out the force the mass applies to the bar and apply all of this force at a single point, distributing it along a line across the bar if necessary. Again, this is an abstraction of reality, as no force can be applied at a singular point, but the bar deflections are relatively small, and we're not interested in the behavior of the bar local to this point. So again, for our purpose, this assumption is good enough and simplifies our modeling considerably. Recording the output from the model at the measurement point is simple to abstract, as we can imagine that the probe of the digital gauge acts over a small area. And finally, we have to consider the material response. Handily here, we've done our test first and shown that the displacements are small and the response is proportional to the applied load. So we can assume the material is linear. Being steel, the linear elastic properties are readily available. Having thought through the problem and rationalized these assumptions, we can now start building our model of reality. For this demonstration, we're only going to replicate the test with the 200-gram mass on the end. But once the model is built, it would be a very simple change to modify the applied force and repeat the simulation for the other two test conditions. This highlights the point that if MODSIM is your mindset, then designing physical tests so that you can take advantage of features like this, where changes to your test scheme are also easy to implement and assess in your simulation, further improves the overall process efficiency. In this case, we're going to use the Abacus solver technology and build our model in Abacus CAE. The geometry of the part is so simple that we can very quickly build the geometry natively in this tool and then start applying simulation features in a logical way. Once we've defined the geometry of the beam from the restrained plane to the end of the beam and partition the geometry to create convenient points to apply the load and measure the displacement, we can assign the elastic material properties of steel to the geometry. Next, we can create a point at which the concentrated force will be applied, and then the coupling that will distribute this force across the width of the beam at the loading plane. We then create a loading step as the container to hold the definition of our loads, boundary conditions, and output requests for the loading history we want to analyze. In this case, our loading history represents the single step for the 200-gram mass being applied to the beam, but could be more complex if required. Once this is defined, we can apply a force equivalent to the 200-gram mass and the fixed boundary condition at the end of the model adjacent to the clamps, which we will assume to be fully restrained. After that, we can mesh the model, assigning appropriate element types as we go, configure the job for the compute resources we have available, and run the simulation. For the size of this job, the simulation time is the order of a few seconds on a desktop PC. With the simulation run, we can start to look at the results by removing the portion of the beam at the free end up to the plane where the displacement is measured in reality. The peak deflection on our displacement contour plot will be equivalent to that measured on the digital dial gauge during the test. Reassuringly, the results indicate the predicted deflection of 0.96 millimeters compared to the test of 0.95 millimeters. It's important to note that for a simulation and test as simple as this not only validates that the simulation we've performed and the approximation made in building that model is a good approximation of reality, but also verifies the underlying solution mechanics of the solver. Indeed, this problem is simple enough that this behavior can also be tied back to a closed form hand calculation to provide a third set of evidence to verify the test if needed. Now, while this problem may be simple enough to solve in 3D, both in terms of the geometry being simple and the solve time being very fast, we can take advantage of further geometric abstractions of our physical geometry to both speed up the simulation further and possibly add more flexibility to play with what-if scenarios. We could abstract our 3D beam to a plane of shell elements where the thickness is another variable that we define as part of the model and can be tuned as it's now not explicitly part of the geometry. If you have a stiffness or deflection target to meet, rerunning the model and changing the thickness value is simple and quick. But back to this problem though, and we can see that even when the problem is extracted to a simpler form, the results are still the same as the solid model and the same as the test result. We don't have to stop there though. For a little more effort in geometric setup, we can abstract our test specimen further to 1D beam elements. Now we need to provide geometric information about the width and thickness of the section. Again, while this adds a little more complexity to the initial model setup, this is balanced by the improved speed of the solution and that all the section dimensions of our beam are now entered as part of the model setup and so can be adjusted if needed. Indeed, there's no reason to be limited to the rectangular section anymore. All set up, solved and evaluated very quickly in the digital environment. But those possibilities are for a real design study. Here we're just looking for confirmation that an even simpler abstraction of the geometry is still valid, and we can show that it is. When we compare all three cases, we can see we get the same result, but with varying levels of user input and model flexibility that may help us explore the effect of other variables. All right, I'll admit that in this case, a hand calculation would tell you all you need to know, but the geometry wouldn't have to get much more complicated with different thicknesses along the length perhaps before a hand calculations become problematic and a structural simulation looks like the best solution. The point of that is that most real world parts are not as geometric simple or loaded as simply as this example. Therefore, while hand calculations may be able to verify rough order of magnitude of displacement or stress, a structural model will often be required to resolve these parameters in sufficient detail to get enough data to make the best decisions. It's also worth saying that with a hand calculation or physical test, you're limited to extracting some data at a single point or the number of channels on your data acquisition system, and inferring from that how the rest of the part is behaving. With simulation tools, you aren't limited to a single point. We've validated our test against a single measurement, but now we can go on and pull out data from the model about how all of the structure is behaving, and so generate more value from the simulation by looking at the total response of the part. So my aim from the previous section was to convince you that relatively simple simulations represent both a viable tool to generate valuable data and that the process is quick and efficient enough to embed in the product design process to generate that data as and when it's needed. The videos in the previous slide show the model being built and solved in near real time. That's great, but my products are more complicated than the steel bar. How can I apply this practically, I hear you say? Whilst that is surely true, I'm glad you asked that question, because we now also need to explore at what point in the design cycle these simple models are deployed and when a simple model of reality is still useful. So thinking about structural simulations you might consider through the complete life cycle of a product, from ideation through detailed design and engineering, all the way up to possibly considering end-of-life disassembly and decommissioning, we could come up with a list that might look a bit like this. This list builds through the design process where the form of the product is taking shape and being married to the functional requirements and consequent decisions are made. This will include thinking about materials and manufacturing techniques and the assembly process of the complete product so that it's ready to supply to the end user. All of these choices have consequences on the structural performance of the product, which may or may not be significant, which should be considered to understand how close to the edge of performance the product is operating at before functional loads are considered and too many choices are set in stone. As such, using simulation to support some of these decisions may be relatively simple and consistently add value for relatively little effort. And some of these scenarios may need more advanced tools or knowledge to provide useful outputs. The overlap may not always be obvious and will vary from product to product, but may look something like this. Traditionally, simulation has been deployed after the product is relatively mature and the design is thrown over the wall to the engineering team to confirm that the design meets the structural performance requirements. That's fine if the design passes, but as we mentioned already, could be a problem if it doesn't. The cost of late change is high. Even if it passes and there is shown to be significant margin left in the design and the potential to optimize it exists, it could be too late by then to take cost and weight out. So while it works, it may not be the best solution possible. All of this underscores the value of having more structural performance data earlier in the design cycle to identify which design parameters are most limiting to the overall structural performance of the product. This stops conservative choices due to lack of data being held in the design until late in the development cycle, where it may be too costly to remove as more of the design is finalized around it. Some decisions may also be dependent on other choices made by other designers or teams. So having tools that can be used to test the combined effect of all these options reduces uncertainty and identifies what the key drivers and decisions are in the performance of the product. What does this actually mean in practice? Well, let's look at a tangible example. Imagine we have this part, which is a step rod known to be loaded in bending in its assembly. In conceptual terms, this is only a few steps more complicated than our validation example of the rectangular bar in bending. But now there are a few more choices to be made as, unlike the bar where we started with a test on an existing beam to validate the simulation, this part doesn't exist. So we are purely using simulation data to drive decisions about the design. In this case, we will analyze the part using a simulation app on the 3D Experience platform. As such, the design of the product and this component will be evolving in a collaborative space on the platform, so we can access the part directly from the designer and place a freeze on the geometry we will work on, perhaps while the design is also still evolving in parallel. While some geometric variables are fixed by other requirements, no doubt some can be changed. Perhaps the fillet radius between the two diameters is a decision to be made, because the designers are aware that as the part will be subjected to bending loads, the fillet will be an area of stress concentration and the stress levels may be too high. The part has been modeled with the properties of steel, and for the purposes of this demonstration, let's imagine the allowable stress from the performance specification is set to be around 300 MPa. As we can pass the evolving geometry from the CAD app directly to the simulation app in the same environment, in the time it's taken me to explain the problem, we've already meshed, loaded, restrained, and analyzed the part, and can see that the stress levels in the fillet are indeed beyond the allowable stress for the material. Again, the complexity of how this individual part might be actually loaded in the assembly has been abstracted, so perhaps we can't get too hung up on the absolute values, but the result is a cause for concern. The value of having created this model is more than this one result, though. We can now quickly modify the geometry to explore the possibilities and limitations in the design. We can see the stress is too high in the nominal fillet radius size, so we can first explore the effect of changing the fillet radius to the largest size the step in the bar can accommodate. This may not be practical, but shows what the best case scenario looks like within the confines of the other geometric variables. As the underlying geometry of the simulation is native CAD geometry on the platform, modifying the fillet radius, updating the simulation, and extracting another result is easy and gives us another piece of useful data, which shows the stress is now just below the allowable stress. Again, important as the absolute value is, it may not be as valuable as the trend in these results, that significantly increasing the radius doesn't significantly reduce the stress. And so this region of the part is a genuine area of concern. To extract as much value as we can, we could also analyze the smallest practical radius dimension to check what the stresses are over the full range of geometric possibilities in this feature. When we do this, we see the calculated stresses are above the notional allowable stress, as expected. More than that, we see that the spread of the calculated stresses is at a high level and over a tight range for the full range of geometric options available. At this stage in the design process, rapidly being able to understand all of this absolute and relative data is incredibly valuable. So what does this all mean? Well, in this simple example, where there aren't too many connected variables, one way might be to look at the range in structural performance relative to the allowable stress in our example component. If we plot the calculated stress as a percentage of the allowable value for the range of possible fillet radii, we can visually see what we already surmised, that the spread of the calculated stresses is at a high level and over a tight range for the geometric options available to us. As a result, the window of opportunity and performance is pretty limited for this one feature. On the other hand, the size of the fillet radius, and so by how much we can reduce the stress level, is restricted by the diameter of the two bar sections. Imagine if we repeat the analysis study, changing a variable at a time to explore the design space from a structural perspective, to help us understand where the possibility exists to change other features to open the window of opportunity for the structural performance of our part overall. If we do that, we might find that changes to other adjacent features themselves have a wider window of opportunity. We can then use this data to start making compromises elsewhere to drive down the stress in our limiting feature. Within this information, we can start making informed compromises, reanalyzing the part in a series of what-if studies to test the compromises and exploring how to open the window of opportunity for each design variable, underpinned by the confidence in the part's performance based on data which takes into account the complexity of the structural scenario we're interested in. While that process is entirely appropriate for our very simple bar example, it's possible that the complexity of the interactions between different design variables makes it difficult to manually identify the best compromise in practical real-world components. This could be especially true if the part is also to be subjected to multiple loading scenarios. Combining geometry modeling and simulation on the 3D Experience platform means that not only is the data associated with all these activities stored in one place, it is also fully connected to the digital thread of the product lifecycle and is available to interrogate, inform design decisions, and revisit later as needed. This digital thread for the entire product creation process can be stored and managed on the platform, including retaining all key information associated with the simulations and how this was used to inform and support design decisions. The benefit of all this data in the context of what we're talking about here is that it can be subjected to sophisticated data analytics directly on the platform to help identify the best overall solution automatically. In the example shown here, topology optimization has been used to reduce weight and explore geometry options in the part intended for additive manufacturing. But the balance of stiffness, weight, mass, and manufacturability has to be considered to make sense of what the best overall solution literally looks like. Compromises between these often conflicting objectives have to be made. All of the design variables explored in the simulations can be cross-referenced and weighted or prioritized relative to one another. This then allows the different possible geometric solutions and the simulation results from these combinations of design variables to be ranked and compared against the required metrics. The results of this comparison can be displayed in different ways depending on the audience that needs to consume the data. As well as the summary of the comparison, the detailed output from each simulation used in the ranking exercise is available in the background and can be pulled up to review in more detail if required. But why limit ourselves to geometry? One of the obvious limitations of physical testing is the time, cost, and effort that's needed to be invested in manufacturing the parts to be tested. Not just that, but often the test rig needs to be designed and built as well. Virtual testing of parts through simulations allows things like material choices to be changed very quickly indeed. The effect of different materials and their particular properties can be evaluated almost as a live activity in the digital world compared to making new parts in a physical test. Back in our step bar example, we've decided to test the effect of changing the material from linear elastic properties of steel to that of aluminium. This can be achieved in a few mouse clicks and the model is ready to reanalyze. Clearly, this is a trivial example because, as expected when we review the results, the calculated stresses in the fillet remains the same, but the displacement at the loaded end of the bar increases in the ratio of the moduli of the steel and aluminium materials. However, the point is to illustrate how easy it is to test a material change when you don't physically have to remake the part. And again, it may not be as easy to predict the outcome of switching material if the part geometry, loading, or the material characteristics themselves were even slightly more complex. But why stop even there? It's entirely possible to virtually test the assembly process and how the parts of your product will come together. This could be in isolation from the rest of the part and the wider assembly, as in this snaps fit example here, where we might want to simulate the assembly and disassembly processes. With this model, we can calculate the forces required to push together and pull apart the clip and check if the material can cope with stresses this creates. Or it might be other assembly features, such as the forces from bolt loads or the stresses due to interference fit between parts. Once we can model these individual actions, we can start looking at modeling the build sequence of the product as a whole to understand how this might affect the way the stresses or residual deformations are locked into the assembly and how that might affect the product's ability to function. At this point, we are nudging into the realm of the specialist, but it's okay if we stop our MODSIM journey here, as a lot of the groundwork has been done with relatively simple models to create confidence that the product is likely to perform as expected before we come to the formal structural sign-off. So if I've managed to convince you that these tools are simple enough to use and the process validated enough to provide useful data, then you're ready to see the benefits of a MODSIM way of thinking to improve your product development process in whatever way will offer you the most benefits. This might include reduced design time, less testing, reduced overall costs, lower weight, less material, better data management, or a combination of all of these and more, leading to better and more competitive products all round. All achieved through a process of thinking about how your product performs structurally and how it can be optimized at the same time as how it looks and functions right from the start of the design process. And if that sounds like something you should explore, over to Jake to tell you how TECHNIA can help you on that journey.
So early simulation and potential process change. We've talked about why you could be looking to change your approach and showed you what tools you could use. So how can you make the best use of the tools that are on offer? If you were to map your end-to-end process, would it look similar to this, or is it vastly different? Many product developments need to call upon the skills of design and simulation engineers to get the job done. But why are they still viewed as siloed roles? How can we go about breaking down these barriers and linking our workflow more seamlessly to get the best end result? The best way to try and incorporate this change initially is to keep it simple. Simplistic models and analyses are also going to give the best early return on investment. Adding complexity takes time, and although it gives you a better definition to the end product, you want to make sure that any early assumptions you have made are going to get to that point and instead are replaced with informed decisions, results, or data. Nothing's ever perfect, even when simulated, but ironing out those variabilities at an early stage is a big win. For example, take a look at this very simple beam problem that we've run to compare effort and runtime. Admittedly, this is a very simple study of a 50mm diameter tube and one that could be completed with simple hand calculations, but it's only there to showcase the difference in computational speed and its alignment with accuracy, similarly to what was shown in the real world testing earlier. Instead of 1D beam elements, you could use 2D shell elements. Anything that takes out nodes, elements, and complexity of a model will likely mean that it runs more quickly and you can make more changes or complete more studies for the same effort. Or more importantly, you can reduce the time taken to retrieve informed feedback. To aid this speed and simplicity, why not look to add a basic simulation stage into your design process alongside your concepts? Studies such as this can be set up so quickly that whether they have a positive or negative result once completed, they make an immediate impact in your design direction. We're not trying to dissuade people from using experts for specific analyses, more to try and democratize the early efforts so that people have more understanding and control on the direction of the development before it starts to cost more if mistakes occur. Investing a little more at this stage empowers your engineers, allowing them to create better designs for more suitable products that are likely to reap greater rewards further along the product design lifecycle. Mastering the basics can be simple with the use of simple step-by-step menus, and simulations can be templated for an analysis by an engineer that's run by an analyst. This is to ensure accuracy and development throughout the process. Once your team has mastered that, they can go on to use automation tools perhaps and extend that learning. So is simulation really required? With the obvious advantages you've heard and seen, you'd be forgiven for thinking that everyone uses this integrated approach. However, often engineers or their managers will give one of the following reasons for their decision not to invest in simulation tools. The products don't break, their performance is satisfactory, and they don't need to improve them. This is common among companies who are trailing in their markets. Making this kind of statement is a sign that they're not forward-thinking enough to push boundaries, or otherwise they don't have enough reference data to truly assess their product. Right first-time design. While it's entirely possible to develop a product that fits its specification on the first attempt, it's impossible to know whether this attempt was the best it could be. The only way to assess a product properly is by introducing a range of reference points via iterative development. These reviews must allow it to converge on the best fit result where improvements no longer occur, where developments show diminishing returns for further investment. Simulation is time consuming. Most engineers think of the traditional approach to simulation, of sending a final design to be analysed once completed. This level of detail means that there are more components taking longer to mesh, debug, solve, and then interpret their results. That old siloed activity we looked at previously, where someone finishes a design and then puts it over the fence effectively for the analyst to work on the final component. When we integrate the process, the level of detail is far lower, but more common. This means that results can be achieved more quickly and make more impact on the product direction. Looking at this image, it's possible to imagine that the area under each of the lines is the time or the cost associated with the effort made. Not having that iterative cycle means that it takes longer to come to a conclusion on something, positively or negatively. It may even mean that you land on a lesser solution as something that works but hasn't been fine-tuned by these iterations. Another thought is that simulation requires specialist knowledge. And although this is still the case in some areas, many engineers believe it's still the case in all areas, and it once was. However, software like the 3D Experience platform delivers simulation tools straight to the engineer to use alongside their traditional 3D modeling apps. The level of integration between these tools has improved tremendously, and now you can get seamless interaction, edits, reruns, and other facilities available to each of the engineers, which makes it far easier to utilize the capability and receive useful results. Specialist roles in simulations are still common in situations requiring more advanced engineering for research and development projects, or in this instance, the complexity of final designs and their need for the experience to assess that as a whole package. But it's far easier for the engineer to take some ownership of these early gains. So are you interested in learning more? If you're interested in learning more about this level of simulation capability, why not view our mini-series on MODSIM, introducing some of the terminology, the basic hints and tips for getting started in designer level simulation. As well as software support, within TECHNIA, we're pleased to have our own group of design and simulation engineers. With countless years of experience across multiple industries and roles, there are likely very few problems that someone hasn't got a history with or transferable skill to deal with. With our existing customer base, we run a buddy system where each account is designated one of our engineers as their first port of call for support requests. Assessed by their software usage or the type of work they are doing, these customers are linked to the most suitable engineer for their needs. Support problems are reviewed with the entire team each week so we can share knowledge and widen the field on certain problems. But ultimately, the benefit of this link means that the issues rarely pass this first stage, as there's a more intimate knowledge and trust between the two parties. One other change we've recently employed is to form these engineering groups into one central team from their previous silos. We found that this has had many positives in our day-to-day efforts when running consultancy projects or providing support for our customers. Sharing issues and projects regularly means there is a common understanding of the problems, more heads to come up with solutions, and more appreciation of the effort required for certain workloads. Probably most importantly for this discussion is that our design bias team have been able to learn some simulation skills and employ those before and during their developments. Clearly, their skills are not as advanced as our power users, but we're continually learning from each other to improve this knowledge and ensure that we gain more and more trust in the process and the results. We've also found many positives from the alternative angle too, in that our simulation team can now call upon design resource to assist in defeaturing or simplifying models at a higher pace because they're more used to the software. But also that our simulation team are learning basic modeling tools on our shared platform as well. It shows a certain overlap if drawn as a Venn diagram, and as that overlap continues to grow, so does the skill set of the engineers and the value of the work being created. So how can TECHNIA help you? So we've talked about why to do it, we've seen examples of what can be done, we've talked about changes, and we've showed what we've implemented successfully here at TECHNIA. But most importantly, how can we help you on your journey? First and foremost, the journey that our engineering team has gone on to develop this level of simulation knowledge puts us in a great position to help you with yours. We've been through the same changes. We know some of the pain points, the high yield areas, the long-term goals, and ultimately we've experienced what we believe you should be looking to go through. So the next big question is what you might need help with. Did the product lifecycle look familiar to you? Do you cover the entirety of that or just a portion of it? Whatever area of this you work in and however you may need support, TECHNIA are likely to have the skill set to help you develop more efficiently. Typically, we find that people sit within one of these categories of service level. In this Venn diagram, you can see there's areas where you have the necessary software, you have the skill sets, or you have the capacity, but maybe you only have a combination of these. Firstly, if you have the capacity and you have the skill set, you're likely to require to complete the work on your own standards, on your own system. And with that in mind, perhaps you only need sales support to show you the best fit products to achieve your goals. You may need some training, but are capable of taking the whole process in-house and just need the tools to complete it. Perhaps you have capacity and the correct software, but not the necessary skills. You're keen to develop your team and ultimately take on these projects, but as it stands, you haven't got the skill set to complete them. You either need some training support or some mentoring from our engineering team. We can build the initial works and guide you through these processes so that ultimately you can upskill and take them back in-house. Perhaps you have the software and the skill set, but no capacity. Perhaps you're struggling with a peak of projects for your team size, or you need some more niche skills that you don't normally have available. This is where our engineering consultancy comes in, and we can support by taking the project off your hand and delivering the end result for you. Now, you may look at this and think that you have all of these in-house. You've got the skill set, you've got the tool sets and the capacity. So what's next? Moving you up to a higher class of expertise means that you could look to utilize some of the more advanced tool sets. Not covered in this talk, but another thing that TECHNIA has a wealth of in its experience is to generate scripts, automated processes, digital developments. Each of these merges with the idea that the typical design life cycle is not so typical anymore, and that many advantages can be had by allowing your digital devices to do more work for you. So what next? Ultimately, most companies will still use a physical test model as their measure of success. Using simulation to mimic this is certainly possible, but not many will invest enough to make this realistic. However, employing simulation-driven design from the outset of the project means that errors are more likely to be caught earlier on, and that means the expensive stage of physical prototyping and testing is more likely to be successful. Not only does it aid sustainability in reducing material usage and wastage, but with the cost of materials increasing and set to continue, reducing usage will certainly pay back quickly. Perhaps we can help you revisit your approach on your products. It's easy to think they're good enough without continuing to explore how they can be better. I'll leave you with this Venn diagram again. Do you see something that fits your scenario? And if so, select the right number and contact one of our team to see how we can help move you forward.